I want to talk a little bit about motion graphs. And I've put a whole bunch of graphs up here, dt, vt, and at graphs. And we're going to separate them into 3 columns. And I'm going to do one at a time, because it always helps to understand how graphs interact with each other. So let's say, for example, you have a distance-time graph that looks like that, right? That is a constant slope. So as a constant slope, that really is just a constant speed problem. Constant speed. So let's graph what constant speed looks like. It means the speed isn't changing, so your speed should look like that. The slope is positive, so your velocity should be positive. And your acceleration, if your velocity isn't changing, remember acceleration is the slope of this, and the slope of this is 0. Tells you your acceleration is 0, so your acceleration is just going to look like that. It's going to be 0. That's one example. Whenever your speed is not constant, and you could have a negative speed too and a negative velocity, but let's say instead your speed looks something like that. Whenever your distance time graph or your displacement time graph is curved, a curve is a sign that you're going to have some sort of acceleration. And so let's think about this. Right here, that slope is shallow, but it gets very steep as you go on. And this slope is velocity. So as you go on, the slope gets bigger and bigger and bigger. So that tells you as you go on, your velocity gets bigger and bigger and bigger. Right here, it's a small velocity and thus a small slope. Up here, a big slope, so a big velocity. And then your acceleration is really just a graph of the slope of this. And so if the slope of this is constant, meaning it's not changing, your acceleration should be constant. Not 0, but constant. So that should not, I'm going to make that even just a little flatter there to make acceleration is not changing. And this object would be speeding up. I can give you an object that is slowing down. So for this one, you see that each time increment, because the velocity is getting bigger, it's going a further distance in a smaller amount of time, it's speeding up. This one's going a smaller and smaller distance every second. So the velocity starts out at a big number, it's steep, and then ends up shallow. So in fact, your velocity is decreasing for this one. And decreasing still has a constant slope, but this time it's negative. So your acceleration time graph might look something, if that's 0, it might be negative like that. If you want a kind of extreme example, it's always fun to think about throwing something up and catching it. What's happening as you throw it up and then you let it fall back down again? Distance versus time. So at first the distance is increasing, but then it reaches the top and comes back down. It's moving less and less up here, so at the very top its velocity is 0. Doesn't stay 0 for very long. So velocity versus time. So initially it's got a big velocity moving upwards. So up here is your big velocity. It's stopped here, meaning velocity is 0, but then it becomes negative. So in fact, your velocity time graph looks something like that. And you don't realize it, but this is a pretty pivotal point right here. This is the point at which it stops going up and starts going down. Velocity is all positive here, but getting closer to 0. Now it's negative. So this is fast, up. This is slow, up. This is stopped. And now it's speeding up and falling. And so even for something like this, your slope is constant. The difference is that it's a negative constant. So if that is the number 0, your acceleration could be negative 9.8 meters per second squared. So this is what the motion graphs would look like for an object thrown up in the air and then falling back down. Thank you very much for watching.